Okay, and we are sharing. All right, so today is algorithm day. All right, algorithms or the algorithm unit is one of the units that we haven't done yet, but you will be fine because we're going to go over everything you need to know about algorithms, and we'll do the unit on them later. The only difference being um, the activities and things like that, which are not a total waste, but this is the stuff you need for the test. So we're going to focus on that. All right. So the documents I'm going to be using, and I recommend you open up, are course vocabulary, which is down here you know, on the page. It doesn't have anything to do with the date there. And the other one that we're going to go through, well, let's just take a look at the course vocabulary thing. So this document is all of the different units, vocabulary words and definitions, of course. And if you know and understand all of these words and have a basic understanding of programming, like being able to keep track of a variable as it changes and what the output would be from some sort of program, that's probably a 3 out of 5 just right there, maybe a 4 out of 5, depending. All right. This is the content. And a lot of the stuff, I mean, we will probably the last day do a quick recap of the lessons or units that we have done, like the internet and digital information, binary, overflow error, that sort of thing. But for now, we are going to focus on the unit. So 10.9 was the create test. Algorithms. All right. So what is an algorithm? An algorithm, finite set of instructions to accomplish a task. It's just the step-by-step process for doing something. We have been making algorithms. We just made them in the form of AppLab functions. Okay. It's just the step-by-step process for doing something. And you could think about the like a filter function. The algorithm is first, wipe the filter list. Second, loop through the main list. At each item, check for what that is the algorithm. You could write it out in paragraph form or you could write it out in programming. It's not anything new. It's just the steps for solving things. And questions on the test are going to give you like maybe steps 1, 2, and 3 out of an algorithm. Say the goal is for this. What is a step 4 that would make the goal successful or something like that, where it's not really asking you about algorithm terms. It's just a programming question that doesn't have any program code. All right, like what would you do first, that sort of thing. Okay, a lot of these words we've seen a bunch of. Sequencing is just the order that things go in, and that there are a couple questions that are going to be, here are the different options for achieving this goal. What is the order you need to do them? Sort by this, eliminate that, resort, that sort of thing. The order of the steps is the sequence. Selection is just a conditional, choosing an item, and iteration is just a loop. Okay. One of the important concepts of algorithms is what's called efficiency, and that is how long it takes to achieve the goal in terms of computing cycles. Meaning, if you have a loop that goes to every item in a list, the number of computing cycles is the number of items in the list. If you have a algorithm that goes to every item in the list and then compares it to every other item in the list, for each item in the list, you need to go to each item in the list. That would be number of items squared. All right. That's not necessarily always possible to have the more efficient ones, but there are times when an algorithm or a problem can be solved a couple ways, and one is a lot faster than the other. For instance, a binary search, okay, as opposed to a linear search. So a binary search is a situation where you are looking for, or when it would be applied, is when you're looking for a particular number in a list. And you want to know which position that number is in your list. This only works if all the numbers are organized in order. But if you have a list full of numbers that are increasing, a binary search does this. It checks the middle number. If the number you're looking for is above it, it then splits the difference and goes to, 3/4 of the way into the list, splitting that top half in half. It then checks again, is it above or below that whatever number's in that position? And it keeps splitting the difference, and it can find the position of the number you're looking for faster on average than just checking every one. Okay, the average number of computing cycles it takes to find a number in a list using linear search is half. However many numbers are in a list, on average, it will be half as many cycles to get to find that, because sometimes it'd be below, middle, and after middle. But on average, binary search is, I forget what the formula is for it based on the number of items in the list. You just need to know it's faster, but it only works if it's numbers and they are in increasing order. All right, so concepts of reasonable time and unreasonable time has to do with this idea of efficient programming. And it's really, there's a couple of questions that we'll get to. It has to do with how fast it scales. Meaning, if you double the number of items in a list, if your algorithm has a linear progression, which is different than a linear search, you double the number of items, you double the number of computing cycles. Linear is good. If your algorithm is n squared, that means if you double the number of items in the list, you have 4 times as many computing cycles. That is still considered okay. If your algorithm is considered exponential, if you double the items in the list, you have 2 to the number of items in the list power. I think that's how it works. I think it depends. But the point is, at that point, the rate at which the number of computing cycles are required increases. It increases too quickly to the point where it's not considered reasonable. But there's another category called undecidable. Don't overthink it, it's what it sounds like. All you need to know is that there are problems that cannot be solved, regardless of how powerful the computers are. There are undecidable problems. Okay, and the concepts of unreasonable or reasonable time are not relevant or not related to the power of the computer. It's this concept of what's called big O notation, but that's not on any of the questions, or shouldn't be. Optimized distributed computing. Okay, so sequential and parallel computing. This is when you can have your computer or have your program, your software, hardware engineering, whatever. Sequential means it's a single path. One portion of the computer has to solve everything. Parallel means 2 paths or more. The problem, parallel is, of course, going to be faster if you have 2 people doing the same, accomplishing all the tasks. It's going to be faster, with the exception of if each task requires the previous task in order to be completed, then you can't have them take 2 rows. It has to be in order, and you would be forced to do sequential. And distributed computing, same thing, multiple devices. Speed up is just the relative increase. The time used to complete a task in order sequentially divided by the time task in parallel. So in other words, speed up is how much better parallel computing is in a particular situation. Other hypercritical parts or words, heuristics. I think we may have talked about this at one point. A heuristic is a what they say a rule of thumb, a general guideline when there is a problem that you have that's super difficult for a computer to solve. Sometimes it's better to just get a good answer and move on, where you might not know what the best answer is, or it might take super long, an unreasonable amount of time to find the optimum answer, or the optimum answer isn't known. We did talk about this when we talked about compression. I'm recalling. If it's a situation where the correct answer isn't knowable, or like the optimum compression ratio, you don't know that you have the most or the best. You could keep looking for a long time and then decide you haven't found one better. Or you can set up a heuristic, which just solves the problem pretty good with the benefit of allowing you to move on. Okay, it's a good enough solution. Okay, so we're going to do a few of the practice questions, and what the documents I'm going to use are these 4 documents right here, starting from all 3 practice test PDFs, which are like I said, the practice tests from the, actually, I'm going to open it in Acrobat. It's easier to sort for me, but you can just, uh-oh. What happened? Oh, no. I just break it. Shoot. Feel free to, of course, open it. Of course, in, a Chrome tab is fine. Like I said, I'm going to open it in Acrobat just to have a little bit more control. And so the 4 documents that we're going to use are all 3 practice tests in PDF form. Okay. And then the 3 documents that I wasn't able to combine, but they are the answers for those 3 tests with explanations. Okay, you'll see it looks like this. Okay, so the full practice test is this one. Ugh. Okay, which is that first PDF, and then we have okay. Let's go with this. And which one is 18? That's 20. That's 21. So that makes that 18. Okay. So these 3 answer links are like I said, the answers to all 3 of the tests that are here combined in a single PDF. But the answer ones are more than just the answers. They explain why one is correct. And it also gives the portion from the full course curriculum where you can look up the expectations, not the code.org course curriculum, but the College Board, which is the full course and exam description, which this is a like 150-page document, but you can search it, so that's good. All right, so let's look at some algorithm questions. Like I said before, the questions are going to be both what are the characteristics of algorithms, like reasonable time, unreasonable time, that sort of thing, and questions where they give you an algorithm or an incomplete algorithm or something like that, where it's essentially programming questions, but not written in code. All right, so let's go ahead and find some. And okay, so also just to make things easier or understand this, like I said, this document is 3 separate tests combined, and you can see that the question numbers go from, we're at 4 here. We go all the way up to like 75, question 75. And then it starts the second test, which is the 2020 test. And then it goes all the way up to like 75 again, question 75. And then it starts a new test, which is the 2021 test. So they're all combined there. But unfortunately, I couldn't combine all of the answer ones. You just need to know, okay, if it's in the top third, it's the 2018 answers. If it's in the middle third, it's the 2020, and the last one's the 2021. Okay, so this is a question where they've given you an algorithm for deciding a ticket price for a movie. And that algorithm, in this case, is written out in chart form or table form. And we need to figure out how to convert this concept into some basic pseudocode. Okay, this is a programming question. It uses the word algorithm, but that's fine. Okay, so first thing would be to try and understand how the actual pricing system works. We have a regular starting fee of 12. If the person is 12 and below, it's important to understand whether they're asking below 12 or 12 and below. Okay, it's the difference between less than and less than and equal to. If they're 12 or below, it's 9. If they're 60 and above, it's also 9. But there is a $5 fee for 3D movies. You're fine. Regardless of age. Okay, so we create an algorithm, set the value of ticket price based on the table. The program uses the integer variable age, meaning just integer, meaning whole number. For the age of the moviegoer, the Boolean variable is 3D. Just means Boolean is a true or false variable. And it works the same way as any other conditional. It equates to either true or false. So going through these, we need to figure out which one creates this. We are looking for $12 to start. And really, a lot of today is going to be multiple choice test taking strategies. And if you just look, first step would be to look at all 4 and look for similarities and differences. They all start with declaring the variable ticket price, which we have talked about pseudocode before, but this arrow pointing back is just assigning this variable, whatever this would be. It's the same thing as the purple single equal sign. So they all start with declaring ticket price 12, right? So we know whichever one of these is correct starts with declaring the ticket price at 12. Now, we need to figure out when to change it and how to change it. So first one is if the age is less than or equal to 12 or over 60, set the price to 9. And if 3D, set the price to 17. Okay. I don't really know how to go over this without giving away the answer, but we'll just go through them. This one is checks to see if the age should be lower and sets the price to 9. But this one is, instead of having sequential if statements, this is an if else. So it can only run this one or this one, which should tell you that that's not going to work because there are 2 different questions being asked here. The 2 questions are, does the age decrease the value? And the other question is it 3D to increase the ticket price? That's what I meant, decrease the ticket price or increase the ticket price. We're asking 2 separate questions. This one we have, we're checking for age and giving the ticket price 9 if they are in that child senior range. And then asking a separate question, is it 3D? And if it is 3D, our variable ticket price gets whatever it was plus 5. This is just ticket price gets itself plus 5. This is what we're looking for. We're looking for 2 separate questions. Okay, just like before, this is an if else. If else can only run one of the 2. And we need to ask both question, so it can't be an if else. Okay, and let's double check here. Let's put this over here. And we are on question 5 from the first one. So let's go ahead and find a 5. And, oh, well, that's not going to work. There we go. Okay, option C is the correct answer. Code segment initially sets ticket price 12 and then changes 9 only for children and senior. Then it checks for 3D. Okay, there you go, question 5. Okay, next algorithm question. Which of the following best describes one benefit of using iterative and incremental process of programming development? Okay, allows for programmers. So this question isn't about algorithms, so to speak. It's asking about development process. One of the answers has algorithm in it. And you'll notice as we go through, a lot of the multiple choice answers are about topics from this year, but are unrelated to the question. The wrong answers, I should say, are, of course, unrelated to the question, but they're not made up of randomly chosen words. They're designed to be, we'll say, a little tricky by using terms or concepts that are from other units and have students see them be, oh, I've heard of compression. This is clearly compression. Not necessarily. Okay, what are the benefits of iterative and incremental process of development? Allows programmers to implement algorithmic solutions for otherwise unsolvable problems. That's unrelated. I mean, there are unsolvable problems, but there's no scenario in which somebody can implement an algorithm to solve the otherwise unsolvable. Okay, eliminates the need for programmers to test complete programs. That's unrelated. Okay, it's asking why is it good to make things, slowly, step by step. Enables programs to keep programs that use lowest level abstractions available. It helps programs identify errors, components, as components are added to the program. Of course, okay? If you're going through things slowly and implementing features and code as you go, you can test and figure out what is the actual problem, or know the new thing is the problem. Okay. Next algorithm question. Okay, so for questions, we're still on the first test, questions 24 and 25. Okay, byte pair encoding is a data encoding technique. The encoding algorithm looks for pairs of characters that appear in a string more than once and replaces them, replaces each of the pairs with a corresponding character that doesn't appear in the string. The algorithm saves a list containing, meaning it keeps track of a list containing all the characters that correspond. Meaning the key is that this is a form of compression. This is almost exactly like the compression widget that we did way back when, where you could see here from the example, this is the starting string. This is the best wish. And when it's encoded, every place that was a TH gets replaced with the % symbol. So there's a TH, there's a TH. So replace two % symbols. And same thing with the IS. Hopefully this is familiar when we did the lyrics to the songs and tried to pick out common things. So the point is, we are compressing it, but we are keeping, or they are keeping track of the replacements. All right. So it can be completely rebuilt to its original. Okay. Hopefully you remember the difference between lossy and lossless. Right. This is, of course, from unit 1, I think, data. But you do need to know there will absolutely be a handful of questions about compression. The key being lossless means it can be completely rebuilt to its initial size. Okay. And so as I depending on the question, it makes sense or doesn't make sense. The reason why I recommended getting out a pencil and paper is because as we go through these, I think there's a tendency to just sort of not necessarily zone out, but just sit and wait for me to say the answers, where there's benefits if you are forced to make a decision and then find out whether or not you're right. And by forced to make a decision, I mean, write down, for your own sake, write down a number. I mean, a letter, an answer. Okay, just a little scribble for your own sake. Give yourself some commitment to decide the answer, and then you'll know, instead of being like, oh, I think it's this one, but it might be that one. Oh, it turns out to be that one. That I do not think will have the same impact as forcing yourself to make a decision. Okay, so we've established that it's lossless. Okay, which of the following statements about byte pair encoding is true? We do know, and I've told you a second ago, it's about lossless. So of these two, okay, first answer, byte pair encoding is an example of lossless transformation because the encoded string can be restored to its original version. Or byte pair encoding is an example of lossless transformation because it can be used to transmit a message securely. I'll give you like 1 second to answer that. Just write down the one you think. Okay, answer is C, because it is compression. Compression is, this is a question of compression. It's not a question of encoding or encryption, which we will talk about encryption. Compression has nothing to do with security. Compression is just making messages smaller so that they take up less space in storage and they're faster to transmit. That is the whole point of compression. We have lossy compression, where you can just, delete every other pixel. It makes the image smaller, makes the file size smaller, and it's probably good enough. Lossless is compressed, but can go completely back to its original version. Okay, so there are going to be a handful of questions where instead of the algorithm be presented you in like a step 1, step 2, step 3 type of thing, or in a table form, like the ticket price thing a second ago, you'll get an algorithm in a flowchart, which may seem complicated, especially if you're not familiar with, the different shapes. But if you sort of understand a few things, you don't even really need to know the shapes. Okay, if it's a greater than or less than or equal to some comparative operator, it's a conditional. It's asking a question with either false or true being the outputs. And if it's the arrow pointing to the variable, it's an assignment. It's just reassigning the variable. Okay, so for this one, a flowchart is a visual way to represent an algorithm. Flowchart is being used by an apartment rental website to set the variable include to true for apartments that meet certain criteria. Okay, so it's going through a list of apartments and checking a few things. And if those things are true, it will say include is true. If it doesn't meet those requirements, include will be false. Okay, so which of these statements is equivalent to the flowchart? Okay, so we have include gets some combination of floor being greater than, less than, and bedrooms being, well, its bedrooms are all equals 3. The difference is being or an and in the middle, and the other difference being less than, greater than for over here. Okay, so we start here and we say, we are asking if the floor is greater than 10, then it goes to true and it makes a direct path for true. So all you really need for it to be true is floor is greater than 10. But if it's not greater than 10, it still checks if bedrooms are 3. If bedrooms are equal to 3, that's true, and it goes to true. So it only needs to be one of these two things in order to make it to true. Which one of these do you think says that? I'll give you a few seconds. All right, so it is going to be A, I believe, unless I'm misreading this. Because the paths to true, there are two paths to true. There is this being true, and it goes to true. But if this is false, it then checks this, and this is, if this is true, it goes to this. So it's either one of these can get you on a path to true, which means it's an OR statement. And of the two OR statements, this first one is checking greater than 10, which is what we're checking. So in order to get to true, it's either floor greater than 10 or bedrooms equal to 3. Okay, hopefully that made sense. Is this the same one? It is the same one. And we're searching. Shouldn't take that long. Let me just double check to make sure I'm not misreading something. This was question 33 on the first test. And yeah, okay, 33, the one we just did. Include is true, the floor greater than 10, or bedrooms equal to 3. So it's, yeah, it's the first one. That's not what I want. Let's go back like that, and we'll go to question this one. All right, so this is what I was talking about before about reasonable or unreasonable amount of time. Here we have it doesn't really matter what it is, but it's an online retailer that uses an algorithm to sort the list of items, or excuse me, yeah, list of items by price. Okay, when they say n items, they just mean the number of items in the list. So it sorts the list by price. Okay, the table below shows the approximate number of steps the algorithm takes to sort lists of different size. If the list has 10 items in it, it takes 100 steps to do the sorting. 20 goes to 400, 30 makes 900 steps, 50 makes 2,500, 60 makes 3,600. It is increasing by n squared. Okay, however many items there are in the list, it is the square number. The square of that is the number of steps. This algorithm's efficiency, or big O notation, is n squared. N squared is considered reasonable. It is polynomial. It is something to an exponent, not the n being the exponent. Okay, so even though the number of steps is scaling quicker than the number of items, significantly quicker, it is still what's considered a reasonable amount of time for a computer to solve. Okay, the other answers, algorithm runs but not reasonable. The algorithm attempts to solve an undecidable problem. This is not an undecidable problem, it's sorting. The question is, as you add items, is it taking too long? Okay, and the last one, algorithm tends to find an approximate solution where it fails to make an exact solution. This is an algorithm, I mean, this is a heuristic, the approximate solution concept. This is not looking for a heuristic. It's saying it's asking whether or not if this hypothetical algorithm is good enough, is what it's asking. Okay, let me double check and make sure I'm not telling you the wrong things. Yes. Okay, the pattern in the table appears to indicate that there are n squared steps for a list for n items. So however many items there are in that table, there are n squared steps. Okay, the number of steps is a polynomial. Okay, something to an exponent. So it runs in a reasonable time. Okay. They don't go into super deep understanding of the different types of algorithms, exponential and linear and that sort of thing. But the idea of things running in a reasonable time is n squared or better. Linear is the best, or I guess finite. Like if you just have to do a certain number of steps, no matter how many items, that's about as good as it gets. But we'll see some other ones here in a second. Okay, so question 46 from the first test. You can tell because we're in the top third. Okay, student wants to create an algorithm that could determine, given any program and program input, whether or not the program will go on for an infinite loop for that input. So we're looking for a program to check for an infinite loop. The problem the student is attempting to solve is considered an undecidable problem. Which of the following is true about this or any undecidable problem? Okay, I'm going to read these and then you can commit yourself to one of the answers and we'll see what it is. Okay, it is possible to create an algorithm that will solve a problem for all programs and inputs, but the algorithm can only be implemented in low-level programming language. Okay, low-level programming language is just like binary or machine code as opposed to, JavaScript. Okay, it's possible to create an algorithm that will solve the problem for all programs and inputs, but the algorithm requires simultaneous execution for multiple CPUs. Okay, they're saying a parallel computing solution will be able to solve this undecidable problem. It is possible to create an algorithm that will solve the problem for all programs and inputs, but the algorithm will not run in reasonable time. And D, it is not possible to create an algorithm that will solve the problem for all programs and inputs. I'll give you another 2 seconds. Hopefully this form of studying is useful. All right, so the answer is D. The key is they're telling you it's an undecidable problem. That's all you need to know. And the answer, it is not possible to create an algorithm that will solve the problem for all programs and inputs. Just knowing there exist problems that are considered unsolvable is enough. And they're telling you this one is unsolvable. There are unsolvable problems. All right, flying right through. Okay, 52 on the first one. Okay, here, this one is a little bit tougher. I'll give you at least a whole minute to work on this. Okay, a program is developing a word game. The word game wants to create an algorithm that will take a list of words and return a list containing the first letter of all words that are palindromes. Okay, words that are same forward and backwards. The return list should be in alphabetical order. For example, if the list of the words is banana, kayak, mom, apple, level, the return list will contain K, L, and M because the palindromes are kayak, mom, and level. They then get shortened to one letter once you find the palindromes, and then those letters get alphabetized. Okay, the programmer knows the following steps are necessary for the algorithm, but not sure the order. Okay, the 3 steps are shorten, which takes a list of words and returns only the first letter. Keep palindromes, sorts by whether or not a word is a palindrome, and sort is alphabetized. There are 3 different options for the order of these 3 things. Okay, first shorten, then palindromes, then sort, keep palindromes, then shorten, then sort, or sort, keep palindromes, then shorten. Which of these will accomplish the problem? Okay, option 1, option 2, option 1 and 2, or option 2 and 3. I'll give you a whole minute to work on this. All right, so hopefully you've committed to a answer. The correct answer is D. Either of these orders will work. Okay, if you first eliminate all the ones that are not palindromes, then you shorten them to just their first letter, and then alphabetize, that's exactly what we want. If you alphabetize and then get rid of the palindromes, or keep the palindromes, and then only keep the first letter, it's still sorted. It's still only the palindromes first letter. But if you shorten the word first, you no longer know whether or not it's a palindrome. Your program can't check for palindromeness, so it can't be number one. The correct answer was D. And again, let me double check just to make sure. 52. Yes, D is the correct answer. Okay. Options 2 and 3 perform the steps in correct order, in a correct order. The order to generate the desired list. In order to generate the desired list, the algorithm performs the shortened step after the keep palindromes. Otherwise, keep palindromes would not be able to determine whether the original was a palindrome. So as long as you don't get rid of all the letters that determine whether or not it's a palindrome before you keep the palindrome, you're good to go in this case. Okay, which of the following best describes the purpose of machine learning programs? Okay, so machine learning is in the category of artificial intelligence, but it's sort of a precursor to it. And I don't know, just as an aside, there, of course, has been an explosion of discussion or use of the term AI, or artificial intelligence. This is just a pet peeve of mine, unrelated to this. People use AI to just describe programming now. The term has been completely diluted. But regardless, machine learning is, and I don't think we've had enough for you to take the answer here, or solve it like the last one. I think that was worth our time. The key to machine learning is that it's about analyzing large data sets and make predictions based on those data sets. Okay, that's the point. Okay, machine learning doesn't automatically translate algorithms from natural language into machine language. That's what programming languages do. It doesn't determine whether an algorithm can be constructed to answer yes or no for all. Okay, this has to do with decidable or undecidable, unrelated to machine learning. And to find the approximate solution problems otherwise considered unreasonable, that's a heuristic. That has nothing to do with machine learning. Machine learning are programs that predict based on patterns in large data sets. And we will talk about that more when we get into the actual unit. Just knowing that machine learning, in fact, I'm going to put this on the what's it called? Vocab. That is too many capitals. Okay, analyzing large sets of data, recognize a problem, and make prediction. There we go. All right. So machine learning, large data sets. That is, I think it's the only question on machine learning in any of these tests. Okay. So we have, go for it. This is a great opportunity to get your pencil out as a like keeping track of a variable type of thing. But here we want this program to output red, red, blue, red, red, blue, red, red, blue. Of these 4 different functions or programming loops, only one of them would have this output. Okay, so I'll give you a second. This is, of course, pseudocode. Okay, repeat is just a loop, and anything indented is what's in that loop. Here, this is a second loop inside of that, and then just another command. Okay, so it's saying do everything in here twice, and each time through, do this 3 times, and this once, and then go back to the main one and do it a second time. All right, so I will, hold on, 3 times, yeah. I'll tell you how I will do the first one, I'll let you do the other ones. Okay, I'll give you a hint, the answer is not A, but while checking A, I know repeat 2 times, so I got to do this the whole thing twice. And each time through, I need to do this 3 times. So I want to display red 3 times, red, 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 and then blue. And go back up to the top, do it again, red, 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 blue. Okay, this loop right here, this code outputs red, 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 blue, red, 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 blue. That is not the output we're looking for. Okay, which one of the remaining ones has the output red, red, blue, red, red, blue, red, red, blue? Okay, even if you don't know how to like recreate this just by looking at the output or looking at the goal, you can do what I just did with a pencil. Okay, so it goes red and blue and then red and then, or whatever the case may be. Okay, I'll give you a minute to do this one. Whoops, I've made a mistake about something unrelated, which hopefully is not that bad. Okay, so just going through these, B says repeat twice. Okay, so this is saying do this entire thing twice, and each time through, we'll do this 3 times. So this is blue, 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 red, and then again, blue, 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 red. Clearly, that's not the answer. This one is repeat 3 times total. Everything in here goes 3 times. This first thing twice. So this is red, red, blue, and 3 more times. Red, red, blue, red, red, blue, which this is our goal. Red, red, blue 3 times. So C is the answer to that one. Okay, so we are now in the middle one. You can tell because we're on, or the middle of the 3 tests, because we are on question 10 and we're in the middle of the sheet. So looking at question 10 here on page 79 of the main document, if you're following along. Okay, more ticket prices to a museum. Following table. Okay, we've got regular ages 13 and up is $10 or $8 and 10 with a guided tour. Children 12 and below is $6 and 8 with a guided tour. Okay, try to completely ingest, comprehend, receive this, figure out what this chart looks like, just explaining it to somebody like in paragraph form. Okay, $8 for regular people, $6 for young people, and regardless, it's $2 more. Whatever their first ticket is, it's $2 more for the guided tour. Okay, that is the hardest part about this, trying to come up with a basic rule or set of steps, otherwise known as an algorithm, for what this is supposed to mean or how this chart works. Okay, a program creating an algorithm display the ticket price based on the information in the table. The program uses an integer variable age, integer just meaning whole number, and we know what a variable is, called age, which is the age of the person, age of the ticket recipient. The Boolean variable includes tour is true when the ticket for the guided tour and false if it's not. Okay, Boolean variable just means true or false variable. Okay, so let's look at these different programs. Cost set to 6. If age is greater than 12 or includes tour, we add 2 and then display cost. Okay, cost is 6. These all start out with cost is 6. That's good. Here it checks for 12 or under. It adds $2. Oh no, greater than 12. It adds $2. Then it checks for tour and it adds $2. Okay, over here we've got it checks for age and then it checks for includes tour, but note that it only checks for includes tour if the person is over 12, but we need to check no matter what. And that's the same issue over here. Okay, we check for age, but then it's an else. So it can only run one of these. We are asking, again, we're asking 2 questions. It's very similar to the apartment question from 10 minutes ago. And that is, we are asking the age for a starting price. And regardless of their age and starting price, we add 2. So it's 2 separate questions, which means it's this one. Okay, we're asking if age is greater than 12, it goes up $2 because it's 6 for young and greater than 12 is 8. And then it asks if it includes the tour and adds another $2 and display cost. Okay, we're asking 2 questions here. And this is the only output that asks 2 questions to everyone. This asks 2 questions, but it only asks the second question if the first one is true. And this is only asking 1 question with 2 possible outputs. And that's how that works. Okay, question 14. All right. So the following algorithm is intended to make a positive or take a positive integer, a whole number, as an input and display its individual digits in order from right to left. For example, if the input is 512, the algorithm should output 215. Okay, step 3 of this algorithm is missing. These, I think, are the toughest questions. This type of question. There will be questions where they say, what line of this code needs to be changed, which is just, it requires such a level of understanding, which I think is the point. But to be able to process these ideas in your head alone without having any sort of, program, I think is difficult. But if you focus on it, I think you'll be fine working through the different options. We are working from a standpoint of one of these is correct and only one. Okay, so we need to understand what a integer quotient is. Okay, does it say up here? Okay, input a positive integer from the user stored in a variable number. Okay, so we're starting with a number. So the integer quotient, okay, divide the number by 10 and record the integer quotient and the remainder. The integer quotient is the quotient. Quotient just means the result of division. Unfortunately, you need to know that. If you didn't know that, you'd be at a big disadvantage. The integer quotient is the remainder of division, not the result of division, but dropped anything after the decimal point. Okay, so if you have 127 divided by 12, the result is 12.7. Hopefully you can do that in your head. The integer quotient is 12 because that's everything after the division, every part of the whole number, and the remainder is 7. Okay, so we are looking for how we divide by 10, which will give you a single decimal tenths, and the quotient, the full whole number, the integer. And how are we going to do that and output just that first number? Okay, just whatever's in the ones, whatever ends up being the 10th decimal. Okay, display the remainder of the number divided by 10 and display the remainder of the number divided by 10 and store the remainder number. Okay, so you would need to break this down in 2 steps. Okay, if our number is 512, and this algorithm is set up for any number, that's the whole point. It's a problem solving to take a number and output its individual digits in reverse order individually. If our number is 512, the first thing we do is divide by 10, which will give us 51.2. Okay, the integer quotient is 51. The remainder is 2. So in order to output this, the first thing we need to do is output the remainder. This will be our output here. Output the remainder and only keep the quotient, the integer quotient. Okay, so then we have the number 51 and we do it again. We go into step 2 because you can see how it says repeat steps 2 and 3. We go into step 2 again. We divide by 10. Now this is the remainder and this is the integer quotient. So the remainder is 1. We want to display the remainder and keep the whole number. So this integer quotient becomes number. And then you could do it again, and that would be the last one. So we are always displaying the remainder and putting whatever whole number is left over back into the cycle, back into the loop. Okay, repeat until number is 0. Okay, so you would need to go through a third time. Okay, so first, what do we need to do after we do our divide by 10? We want to display the remainder. Good. And store the remainder in number? No, we don't want to store the remainder in number. We want to store the integer quotient, the whole number. Okay, we do want to display the remainder, which every time through will be the next number. And then store the whole number. I want to say remainder because it is remaining. But if we store the whole number back into our number variable, we can then send it back through the loop and move the decimal over again and keep the next one. Okay, so we're only worried about things that are to the right of the decimal after the division, and that's what's going to print out. Okay, so the answer here is this sort of thing. There are, like I said, this is one of the harder questions, but try your best, obviously. Okay, let's get through a couple more of these. Okay, 23, flowchart. Flowchart application used by an application. Set the Boolean variable available to true. Did we just do this one? Is this a different one? No. Okay, it's the same basic idea as that apartment decider thing, but it's a different flowchart. So we need to figure out what is the equivalent programming pseudocode. What is the equivalent for this this flowchart? Okay, so our goal is to get to true. How do we get to true? Well, true for the whole thing, available true. First, it checks is weekday is true. If it's false, we go straight to false. So it has to be weekday is true in order to have a chance of getting to true. If this one is false, it ends. It's over. Okay? Then if this is true, we then need to check if miles is less than 20. And even if this first one is true, if the second one is false, it also takes us directly to false for everything. The only way to get to true is if this is true and this is true. I know that pretty much gives you the answer, but As far as of the and options, there's available if it's weekday. Okay, when you see a Boolean variable, like in this case, weekday, it will just say if weekday. We've done some things like this. It doesn't have to say if weekday equals true. If the variable is a true or false, a Boolean, you don't have to say if weekday is true or if weekday equals false. You just say if weekday. So there are two and situations. Okay, and don't overthink it. It's asking it, or in order for it to be available, it needs to be a weekday and miles have to be less than 20. The hardest part of this one is figuring out whether it's an and or an or situation based on the paths. I don't know how somebody would get confused about greater than versus, flipping the comparison operator. I suppose it's possible though, especially if people are guessing. Okay, so following the flow chart is a skill. Okay, which of the following best explains why it's not possible to use computers to solve every problem? Okay, I'll read these and I want you to commit to an answer. Okay, current computer processing capabilities cannot improve significantly. Large-scale problems require a crowdsourcing model, which is limited to the number of people available. The ability of a computer to solve a problem is limited by the bandwidth of the computer's internet connection, and there exists some problems that cannot be solved using any algorithm. I'll give you about 3 seconds to answer that. Maybe 5 seconds. Okay, this is simple. There exist problems that cannot be solved by any algorithm. This is a concept that you just need to know. There are undecidable problems. There you go. And that is why it's not possible to use a computer to solve every problem, because some of them are unsolvable. That's it. That's your takeaway. Okay, so binary search, we talked about this before, is a search where it splits everything in half and then looks for the next one. But the problem with which of the following conditions must be met in order for the procedure to work as intended: the length needs to be even, the number of lists cannot contain duplicate values. Okay, well, this particular search is looking for the same thing, and looking for a particular number on a list, and it is -1 if it sets it to the procedure returns the index where the target occurs in the list, or it sets it to -1 if it doesn't exist. Like if it gets all the way to the end and there's no none of the targets in the list you're checking, it would set the output to -1. Just that's how that particular algorithm is set up, or procedure function. Which of the following conditions must be met in order for the problem procedure to work as intended? Okay, the length of the list needs to be even. So the binary search starts by taking the list of numbers and finding the middle one. It doesn't have to be an even number to find the middle one. In fact, there's only technically a middle one if it's an odd number, but a binary search knows that if it finds a middle, takes the length divided by 2, and there's nothing at that integer or at that index to pick, the next one. So it doesn't have to be even and the length of the list doesn't have to be even in order to do the binary search. Okay, the list num list cannot contain duplicates. That's not an issue. Num list must be sorted in order. Yes, in order to do a binary search, the numbers have to be sorted in order, pre-sorted. Okay, and the value target must not be equal to -1. It doesn't matter if the thing you're looking for is a -1, because the output is just going to return the index. It's not returning the target. You know the target. So it doesn't matter if the target is -1. It is using that little trick of having a negative number output as the index, since you can't have a negative index. It's another way of returning doesn't exist. But either way, key takeaways are, for a binary search, it needs to be sorted, needs to be pre-sorted. Okay, so we'll do one of these, and we'll try to focus on questions that are more about algorithms, not like just programming. And they say in this algorithm, when it's really just what is the output of the program code, like the red, red, blue, blue thing. That isn't about algorithms. That is just a programming question, which is, useful and everything, but we have limited time. We need to get everything about algorithms done today. Okay, considering the following algorithms, each algorithm operates on a list containing n elements where n is a very large integer. Okay, algorithm 1, an algorithm that accesses each element at least twice, or it accesses each element in the list twice. Okay, an algorithm that accesses each element in the list n times, and an algorithm that accesses only the first 10 elements regardless of list of size. Okay, if it's each element twice, if you double the number of items in the list, you double the number of steps. If you triple it, you triple the number of steps. That's fine. That's great. That's about as good as it gets. Okay, a longer list means more steps, but it's however many steps increased is linear compared to how many steps it was, or compared to how many you're adding, how many items you're adding. Okay, if you're accessing it n times, that means that's a situation where every item you're comparing every item in the list to every other item on the list. So it goes to the first item, checks every item, like for matches or something, then goes to the second item and checks every item, goes to the third item, checks every item. That is n squared. The number of items, however many items there are in the list, there are that many items times itself, number of steps to complete the algorithm. That is still fine. Okay, n squared is fine. Okay, an algorithm that only accesses the first 10 elements. Well, I mean, this is like more efficient than any realistic algorithm to only do the first 10. I mean, there's obviously a scenario where you have a sorted list and you're only interested in the top 10. This is like finite. It doesn't matter how much you add to the list. It's not going to increase the runtime. Okay, so the answer here is all three of these are fine. All three of these are examples of things that run in a reasonable amount of time. Okay, let's double check and make sure I'm not giving you wrong stuff. It's question number 50 from the middle test. Why are we doing this? Just go straight to 50. Page up. 50. Yes. For an algorithm to run in a reasonable time, it must take the number of steps, a number of steps less than or equal to a polynomial function. Okay, algorithm 1 accesses elements 2n times, twice for every element in the list, which is considered reasonable. The second one accesses n squared elements, the number of elements in the list times the number of elements in the list. And the last one accesses only 10 elements, which is considered reasonable also. So all of these are considered reasonable. Okay, let's see if we can find another one like that question talking about reasonable and unreasonable. Okay, this one is very tough. Okay, so I would say we're not going to do this one together, but you should do this one. This is number 55 from the middle test, which, of course, there's an answer on the answers for the middle test. Take a second and look at this one. Try to internalize it. It's actually kind of complicated. But it's an example question. It's the type of thing that you will see on the test. I mean, these all are, but okay. So this one is a little bit easier, but they give you an algorithm But this is really more of a programming question where you're keeping track of things as the program runs. Okay, so this is a game or whatever where there is a board consisting of however many that is, spaces of the different colors. And you are supposed to follow these steps and find out what the value of the counting variable is when you get to the end. Okay, so what do we need? We need, okay, following indicates how the program is played, continues either one by landing on a red space, or the piece goes off the board. Variable shown, various colors shown. Okay, so place the game piece on a space. Does it say what variables we need to keep track of? No. Where is Oh no, that was something else. Okay, so we have a counting variable. Okay, place the game piece on the space that is not red. So this is where ours is starting. Set the counting variable to 0. So we're saying counting is 0. Okay, if the game piece is on a yellow space, move 3 to the left. Otherwise, if the game piece is on a black space, move the game piece 1 to the left. Okay, so we move it 1 to the left. We're here. Increase counter by 1. Counter is now 1. If the game piece on the red or off the board, it's game over. Otherwise, go back to step 2. So we're here on step 2. If we're on a yellow space, move 3 to the left. We are. So we'll go 1, 2, 3. And we jump to here, increase counter by 1. So counter is now 2. We are not on a red or off the board. We go back here. Okay, if the game is on a piece is on a yellow space, move 3 to the left. 1, 2, 3. Increase counter by 1. Counter is now 3. We are not in one of the end game conditions. Okay, and so we go back here. Yellow 3 to the left, black 1 to the left, and green 2 spaces to the right. Okay, so we're here. Let's go. We're on a green, so we go 1, 2. We are now here. Increase the value of counter by 1. And it's game over because we're on a red space. So our final result is 4. The final value of counter is 4. That is not very difficult if you have scratch paper. That's all you need to do to solve it. Just keep track of things as you go. Okay. All right. So this is a question about encryption or cybersecurity. Which of the best explains how device information is susceptible unauthorized attacks if weak passwords are used? This has nothing to do with algorithm or compression. Okay, this is a question about cybersecurity and encryption. So we'll deal with that when we get to that day. Okay, parallel computing. This is a good algorithm question. Okay, how many more we have? We'll just fly through this one. Okay, which of the following best describes challenge with parallel computing solutions? Parallel computing solution may not be appropriate for an algorithm in which each step requires the output of the preceding step. There it is. There is no better description of the flaws or the shortcomings of parallel computing than the fact that you can't have 2 people. Like if you have 10 different tasks to do, you can't give half to one person, half to another person, if in order to do any one of them, you need the result of the previous one. You wouldn't be able to go through all of them if each one needed the previous one finished first. Obviously, if they can be done in any order, having 2 people work on them is better, but it can't work if it's that condition. Okay, just for fun, looking at the other ones, parallel computing solution may not be appropriate algorithm if the same formula, which is the same formula applied to many numeric data elements, irrelevant. Parallel computing solution may not be appropriate for an algorithm that can be easily broken down into smaller independent tests. In fact, that's a great reason to use parallel computing. If they can be small independent tests, that's fantastic. And parallel computing solution may not be appropriate for an algorithm that searches for occurrences of a keyword in a very large number of documents. No, again, another thing. You would rather have two people looking through a huge book for a particular word than one person. Okay, that is when you would want to use parallel computing. Developers have. Okay, so we will talk about bias. This is more global impacts. This is essentially a different unit, but they will talk a lot. There will be a few questions about this category of things, specifically bias in design. And two of the biases that they like to focus on most are age and geographical location, as in young people doing a certain thing versus old people, and rural access to the internet and other tech compared to urban access. Okay, the digital divide is obviously impactful on people that live in the middle of nowhere. And this is not about algorithms. This is, like I said, about biases. And you can work through that one. I'm not going to read the whole thing to you, but that is that. Okay, so this one is another programming one more than an algorithm topic question. But as long as you can follow the flow chart and keep track of the variables, okay, so we have three different things to keep track of here. Okay, we have the value of result, which on the very first line is 0. And then it's our assigned integer values. It then checks for if the value of k is 0. If k is 0, it goes to true. And if it's not, result gets result plus j. And k goes down by 1. Okay, it sounds like a lot, but we'll work through it. Okay, which of the initial values of k, j, and k will cause the algorithm to represent the flow chart to be an infinite loop? Okay, here is for the first one, j is 5 and j is 5 and j is -5 and k is 5. How would this run? Go ahead. Result 0, good. Is k 0? It is not. K is still 5, so it goes here. Result gets result plus j, so our result 0 plus -5, -5, and k goes down by 1, so k is now 4. We run back through the loop. It asks if k is 0. It is not, so result gets result plus j, which means it's now -10, and k goes down by 1. Oh, no, that's j, excuse me. K goes down by 1, so k is now 3. Okay, and as it goes around, it will stop when it gets to k is 0. It's asking of these four possible starting, which will never end, which would never end the loop. Okay, I'll give you a minute to think about this. And this one may actually not be the best one to keep track of with pen and pencil or pencil and paper. More think about what would cause a loop to go on forever. Okay, we haven't had to deal a lot with infinite loops because of the way that the app level. Okay, so the key is the conditional that ends this loop is when k is 0. The only way that k changes throughout the program is going down by 1. If you start out with a negative number and keep going down by 1, k will never equal 0. it will just keep going around and around. K will keep going down by 1. J will be going up, or result will be going up by J, and go on forever. Okay, so the only one of these possible outcomes that would cause an infinite loop is the one where K starts in the negative. Okay, this is that same thing, algorithm. Okay, based on the algorithm. Okay, so this one would make sense to follow along. What would be displayed? Okay, so the display is result. What would be display if J started as 3 and K started as 4? That's one where you can get out your pencil and walk through it step by step, like we've seen. Okay, more of this, same thing. Okay, company delivers packages. This is a good one. I think it'll probably be the one that we end on. Maybe we'll see. Okay. A company delivers packages by truck and would like to minimize the length of the route each driver must travel in order to reach however many items there are, or however many locations there are. You should see this and immediately be reminded of a problem, a famous problem called the traveling salesman problem. And in the traveling salesman problem, the idea is there is a salesman who wants to get to however many different places in the shortest amount of travel time or travel distance. The problem is to find every possible route from every possible starting point is an unreasonable problem. Okay. From any position, you would have to have a different, keep track of the length of the distance to every position, and then continue from each one of those positions to every remaining position, and then to every remaining position from each one of those positions. And it ends up being n factorial, I believe, which is super inefficient. As the number of locations grow, it grows faster than programs can keep up with. So the traveling salesman program or problem is considered unreasonable amount of time to solve. And so the company is considering 2 different algorithms, 2 different problem solving steps for determining the routes. Okay, algorithm 1, generate all possible routes, compute their length, and select the shortest possible route. The algorithm does not run in a reasonable time. This is what I'm talking about. Obviously, to find the shortest route, you could figure out every possible route and keep the shortest one. But as the numbers grow, or the number of locations grow, it takes too long to solve all the possible solutions. The second problem-solving solution, starting from an arbitrary delivery location, find the nearest undelivered location, continue creating the route by selecting the nearest unvisited location to all locations visited. The algorithm does not guarantee the shortest possible route, but runs in a time proportional to n squared. Okay, which of the following best describes, best categorizes algorithm 2? Okay, the closest available. Algorithm 2 attempts to use algorithm approach to solve an otherwise undecidable problem. Nope, this is not an undecidable problem. It is an unreasonable solution or unreasonable time. Algorithm 2 uses a heuristic approach to provide an approximate solution in a reasonable time. When you have a problem that is unreasonable, you can use a heuristic, or your program can use a heuristic when it makes more sense to find a good answer instead of the best answer. And that's what's happening here. The trucks are finding the closest remaining and going to that one. It will end up with a relatively short path if you're only taking the shortest, or only going to the closest remaining, but based on all possible distributions of the location, it might not be the absolute fastest, but it will be fast-ish. And that is the point here. We are coming up with a good enough solution when the alternative is unreasonable or undecidable. Okay, algorithm 2, just for fun, provides no improvement since neither runs in a reasonable time. No, the second one does run in a reasonable time. They say it runs n squared, which is reasonable. Okay, algorithm 2 requires a much faster computer. No, reasonable and unreasonable has nothing to do with computational speed. It is an algorithmic situation. Okay, and I think that's probably the last one. Student development algorithm. This one is good too, but it's not about, this is like the palindrome shorten situation where they're asking which of these orders of steps will come out with the result. It's a good one to work on your own. And okay, which of the following best explains the ability to solve programs algorithmically? Any problem can be solved algorithmically, though some problems may require humans to validate. Okay, first of all, look at this. Any problem can be solved algorithmically. Any problem can be solved algorithmically. Any problem can be solved algorithmically. There exist some problems that cannot be solved algorithmically. That's all you need to know. That is almost definitely going to be a question on the test. There was one, we've already seen it once on the middle test, I think. Knowing that there are problems that exist that cannot be solved. There you go. There's a free point, knowing that. Okay, and I think that's probably where we're going to stop. Okay, here's another one. 53 is one of the fill in the blank with the lines that matter, or the lines that make it fix. And I think that's going to be it for algorithm cram day. I didn't use a lot of the answer sheet to check things, but you should probably be using both documents for your studying. Okay, especially for the ones that you don't know. All right, so that's where we're going to end it. We'll pick up with encryption next time.